Should I copy my file to the computer?
Sure.
Good morning, everyone. Today I will review this article, a survey of the sensing and control systems for machine and process monitoring of the directed energy and metal-based additive manufacturing. So this is the outline. We have the 3 chapters. The first is the AM processes and subsystems that they had been mentioned in this class before, and chapter 2 is the sensing and control of the machine variables, including the laser beam delivery and chamber environment, feedstock delivery. And the third chapter is the sensing and control of the build attributes. That include the melt pool geometry and the temperature, deposition, head, and optical emissions, and path control. So let's go to the fourth chapter, the AM process and the subsystem. So here, the finger shows the first one, the A is the laser-based powder feed, and the B finger is the electric beam and well-fed directed energy deposition processes. And both of this kind of the AM systems, they can include the laser or the E-beam and beam delivery system, and the motion control for the substrate, and the feedstock delivery system, like give the powder or give the well. And lastly, the environment controls, because both systems need the gas for the protection. And here, the potential can use both sensing and feedback control for each subsystem. And the typical variations during the AM systems include the substrate position. So if the substrate position variation can from the misalignment or the powder flow, and powder flow because can be caused by the chamber bag pressure change or the powder clogs or other instabilities, and the laser environment density at the surface can change by the misalignment of the laser beam or the contamination of the powder or the substrate. So from these variations, we need to investigate for the sensing and control for the machine variables. Typically, they use the single input and single output loops. And the fourth section is about the laser beam delivery. That The variations for the laser energy variation can due to the three reasons. First is the internal and external laser beam power fluctuations. And for these researchers, they have developed the two methods by the tuning mirrors or the relay scatter just to control. And here is the finger shoots and optical systems that it can monitor the contamination of the beam delivery by the optics. You can see that from the here at the inside incident laser, and then the reflection of the laser can go to the here that is the motor. It can measure the reflection. So from the change, so if the distortion of the lens or just the contamination, that will change the reflection of the index. It may give the difference of the laser reflection, so that we can measure these changes, so that we can know the somehow the damage to the lens. So, and for the changes in the second is the changes in the lens geometry and the reflection index by the thermal loss. So this is usually caused by the high laser power, and this effect can be reduced by the active cooling. And for the optical, and the third is the optical elements damage. That's for the lens to focus the laser beam. And this for this usually caused by the laser to the substrate. It can give some the vibration or just the gases emission that will affect the lens. So usually they will give a lens protective gas to protect the lens. And the second section is the chamber environment. Usually they monitor the oxygen concentration by using the trans oxygen sensors, and also the chamber pressure fluctuations will influence the feed rate of the powder and the flow rate of the processing gas. The third section is the feedstock delivery. So for the AM process, we want to achieve the consistent quality. So the system requires a well-defined volume of mass material feedstock, and it should be at the appropriate to the correct location. So here there are two methods. One is the real-time monitor the powder flow by the imaging method. Let's say here. Here is use the two cameras. And we can see compare the two white circles in the middle and the right images we can see here in the middle. Here we can see that the light reflection from the powder flow, but for within this circle there are no light reflection from the powder. So we can recognize that there is here the nozzle is clogged. And another one is the real-time monitoring and control of the feed rate. This is by the measuring the attenuation of the laser beam, because when the laser beam passes through the powder, there will be some attenuation. So by measuring this change, you can know the attenuation will indicate the powder feed rate. And the third chapter is about the sensing and control of the build attributes. The first section is about the melt pool geometry. And monitoring the melt pool geometry can help as to assess the build consistency. But here, this figure should coaxial thermal images of the melt pool, like without powder feed stock control. But here is the y-axis, this is the x-axis. So you can see here, this is the actual picture, this is the y-axis, here is the x-axis. So from here, that along the positive y direction, we see that the melt pool width increases here, but the melt pool along the x-axis, the width greatly varies. Let's see here, and even from the actual picture, that this variation, the greatly variation, can relate to the variations for the fellow build heads. Let's see here, the heads are different.
So do they give an idea why there was such variation in the x and y direction?
It does not give the reason that they mention that this can monitor the difference and the variation, the multiple geometry variation that can relate to the fellow height variation. But for these people, they do not give the reason. And others, there are others. The melt temperature can also helpful. And usually, the average melt pool temperature can be readily measured by the sensor. And the diversion head, which is mentioned, this is strongly influenced by the distortion and the changes in the powder capture efficiency. And the head melt we can use the optical sensors, like just for example, TIS1. Let's use the head control system based on the chromatic aberration techniques. It just use during the different heads, it will give the different intensification of the spectrum within the certain working distance. And for the case 2, to have a hybrid control system include a master head control and a slave the melt pool temperature control. So they use 3 high-speed CCD cameras to measure the melt pool height, and they use 2 pyrometers to measure the melt temperature. And when for here, when the melt pool head exceeded a certain point, the temperature control will be blocked and reduce the laser power to limit the fellow head and the build height. And if the melt pool head is within the certain range, the melt pool temperature, so the laser power will vary to give some constant, relatively constant build height. And the fourth is about the optical emissions. Because during the process, they will give the at the surface of the substrate, they will give there will be melting and also the gas vibration. So the two parts, the optical emissions and the vapor emissions. These are related to the temperature and composition of the melt pool. And the fifth is the path control. The advantage of the path control deposition is that the controller will give the less variation in the microstructure than the non-controlled deposition. If we by evaluating the code section of the build. And here, this shows the changing controller activity in the changing hash order during a build. That means that this is the hash order can be programmed, and you see that the layer 1 and the layer 5, they have the different hash order. And this was the so the process is that the procedure that before giving exceeding giving hash, the parameter will measure the substrate temperature first. If the temperature exceeds the certain point, the hash will be skipped until later, and next is programmed hash will be processed first, and then after all the acceptable hashes all processed, the hashes that has been previously skipped will be processed. So by here, this could be give the better nice variation. That's all of my presentation.
Questions?
I guess I just don't get what you mean by hash order.
It's just the laser or the E-beam that the hash order. Also the E-beam goes well which location first and which later. That's the hash order.
So, but red starts somewhere in the middle and then it goes up and then moves down.
So this.
That's one, right? Red is one.
Yeah, red means the first hash, and the laser point grabs the first, and then later is the order. So for the layer, this just goes from here and then go to the bottom. This is for layer 1, but for the layer 35, it goes here first, then compared to the layer 1, they skipped here because the temperature is pretty high. So they go to the next position. And
I just don't see the contour in the 35. Like, I see the whole spectrum kind of in layer 1. I don't know if it's few color. Maybe I can't see it.
They do not. I mean, they do not.
There's no, I don't see the specs. I don't see the.
And a lot more greens than you would expect in pure purples, right?
Yeah, those seems like solid color.
Yeah.
And this one seems like the whole.
oh, maybe.
I don't know what they're looking for.
The contrast of the projector is
maybe
lower.
it's hard to see,
But it first it here and then goes here and goes to top the bottom, and it skipped here and then here, and after finished here they go to this one, and then it go to the middle and go to the top.
So I just have a question about, I guess it's a matter of, if you're going to change something in a process, then evaluating that it had some sort of positive effect. So so they're showing that they made a change in the way in which they scanned the different rows or hatches here. Did they go back through and then after that see if there was a improvement in the process by doing that? And how did they validate those?
For here they valued the microstructure by cut the cross section of the build.
Yeah,
to see the variation.
They did look at microstructures.
Right.
Okay. And there was an improvement? And how did they quantify improvement?
I think they not quantified, not quantity defined, just quantitatively, quantitatively, just compile the visually compile the max structure consistency.
I think it's had a different paper for that specification. So does it mean it didn't develop this path control?
This is a survey article.
Oh.
So, because this was a survey article, and I kind of took a look at all of the different control methods and ways in which you can, use optics or control methods in order to kind of change the process during the build. Did they have any suggestions for a, clear-cut best way for this kind of printing in order to actually go about that control? Because it seems like they showed a lot of various ways and kind of showed the differences between them. But just based when I read it,
So
clear-cut test way to go about controlling the system.
this article does not give the best practice for the each AM process. They just give some excited techniques for all the methods for each specific questions or the problems during the manufacturing.
Can you go to slide 5? So what I was missing here, so was this actually, the case of figure 3, we were looking at how you have a clogged nozzle. This is just monitoring, right? They weren't actually doing anything about the clogged nozzle. They're just noting or understanding using a little bit fancier sensors than you normally have if you have a clogged nozzle. Is that the purpose of this?
They just this is just assess whether there is the clogged nozzle or not. So this is for this method, for this finger shoes.
So they were just monitoring the process, right? They're not actually controlling anything.
No, for this finger they do not. And this one is for control.
Yeah, this is basically controlling speed.
Right. Any questions?
All right, thank you. Okay. So this is just a reminder that a week from today, we're going to have a tour of CDME. So this is their Center for Design Manufacturing Excellence. The person who's going to be giving the tour has told me that he will try his best to make sure the machine's running that day. So he's trying to coordinate everything that goes along with that. I think there should be no issue with access. He basically needs a list of nationalities so they can have a complete record of everyone who was intended to be there, and everyone's got to sign in, etc. But this is the Center for Design Manufacturing Excellence, who I think a few people have been there before, right? Show of hands. 4 people? Okay. For those of you who have not, this is the location. You can search up online. Because of strange university laws, I can't drive you out there, okay? Because they're not going to cover me in case there's some sort of car accident or something like that. So, is anyone going to have issues accessing CDME? Yeah. Yeah, so they have the buses that take you to the West Campus parking lots. Will get you to about, where does it go? It will get you to right here. This is one of the bus stops where my cursor is, and so you can walk from there if there's an access issue. If you have Ohio State parking passes, you can actually just park right at CDME without issue. But it's going to be in the exact same time as a normal class period, so from 9 to 10:20. I have yet to see their new AM suite. The last time I was out there and actually toured their facilities, they had a bunch of AM machines in different locations, and they've actually put in a few $1 million in equipment since I've been out there last. So I'm excited to see this stuff as well. The person who's going to be giving us a tour is Ed Herderick, who is, I don't know his complete background, but he was at GE Aircraft for many, many years. He's one of alum of Ohio State. He got his PhD in material science from Ohio State. Then he worked for GE Aircraft for many years. And then he was in the position at GE Additive at a pretty high up position. I forget his exact title, but he was giving basically talks on behalf of GE Additive at, say, big meetings like American Makes meetings, et cetera. So he was pretty high up at GE. Somehow we lured him here. I don't know how. I guess maybe he wanted to move back to Columbus and whatnot, but he's the person who's going to be giving the tour on Thursday, and he runs a lot of the machines and interfaces with a lot of industry partners who use the machines out at CDME. Yes?
Is there parking if we don't have a student parking pass?
There is, yes. Let me follow up with Ed on that one, but I do know they have, when you sign in, they have like a parking pass sign in too, where you have to put down your license plate number and things of that nature. Anyone else in the same boat where you do not have Ohio State parking pass but have a car? Okay. All right. Well, I'll follow up in an email too as well, so everyone is on the kind of same page. But that's going to be a week from today at 9 o'clock. Okay. And hopefully they have things running. So it'll be cool to see. I've never seen an E-beam system running in real life. I've seen plenty of laser systems running in real life. So hopefully they have the E-beam system running, which that actually probably isn't all that interesting because you probably can't see anything going on, but in a vacuum. But the laser ones they have windows usually, you can see what's going on. Okay. Other things, logistics. Homework 3 is due on Friday. A few students asked if I'll be having office hours today. I'll be here. If anyone can meet right after class, I'm going to be going to my office. We can talk that with any remaining questions on the homework assignments. I can meet then. Okay. All right. Okay, so this is where we ended on Tuesday class. We looked at some simple examples of residual stress in terms of how to calculate with the residual stresses with respect to having some sort of yield stress in the material. And then we went back and looked at this case study. Again, reminder, probably should put on the slide, but reminder, these were disc shape artifacts. Okay, this where it was, these were 45 millimeters in diameter and 5 millimeters tall. It was a disc shape artifact, and we saw via neutron diffraction, we saw this type of this level of residual stress. So just to note, these are, we have the open circle, open markers here are simulations, and then the closed ones are actually experimental results received. Okay, so the general idea here, and this actually relates pretty well to the residual stress paper that Ryan presented, is that you have predominantly tensile residual stress in the part. At the edges, of course, this residual stress has to be 0 because it's a free surface, essentially. And then you have kind of a general sinusoidal or cosine shaped residual stress pattern along one of the directions. And this would say be the y direction. Okay. And then in general, a compressive or slightly or close to 0 or compressive residual stress as you get close to the build plate, right, where the material is being adhered. So this would be our side of the disc. This would be into the plate down here. So this would be the plate below. Right? Yes.
Did you investigate any particular reasons why the simulation seems to not capture the effects close to the build plate or in the lower layers, as well as in the middle and at the top? Because it seems like the other trends kind of follow.
Yeah, and that's where it
pretty,
deviates.
Yeah.
That's where it deviates some. So we don't, no, that's a good question. That was one of the primary questions in the review of this article. We don't have a really good explanation for that. This matches observed results in terms of having some sort of compressive stress near the build plate. But no, we don't have any great explanation for that yet. Yeah, I agree. That was one of the shortcomings of this. Yeah. And I think the rebuttal actually in this submission was something to the effect of, we recognize it doesn't match perfectly, but erring on the side of full disclosure of the results, we still want to put them in there even though we don't have an explanation. Mm-hmm. There's a tendency in, I think, every field to show only results that match perfectly with your simulations, et cetera, because you don't want to show any flaws. And so we said that, yes, we realize this doesn't match perfectly, but we think it's better to show everything as opposed to only showing everything that works out perfectly. Okay. All right, so that's some observations. This is then kind of looking at observations that are similar across different literature. And then I wanted to get back into this observation too. This is actually in a different paper that we published that has a little bit more information than that first work I showed. So this is this other paper we published was purely an experimental paper. If you look at these experimental points and compare it to the one with simulation superimposed, you see that the data is exactly the same. This is coming from exactly the same print. We were just focusing more on the experiments here and nothing on simulation. So this is the same basic trend, but there's now 2 different time points that are of interest. So there's on the build plate, so this is when it's still being fixed, and it's held such that there is essentially no distortion. There is some distortion that's actually measurable that we could pick off with like a CMM, but the distortion is quite low because it's being rigidly held to a really, really thick plate. And then you can release this, in this case using wire EDM, to release the part, and then you can see then what is the stress profile once you release it. And so just like our simulation showed, there's an obvious reduction in the stress level in the part, but you also notice a flipping of the stress as well. Okay, so just to go through here, This is, again, this is negative stresses, this is compressive, right? Positive stresses, this is tensile. All right, so if we look at regions that were low, in terms of low Z height, those were somewhere in the modest compressive stress ranges, and then ones that are high, in this region, they were in the highest stress levels, and they were tensile. Right. And then we release this from the build plate, and then you look at, you can see that now the areas that were low, in terms of Z height, are now tensile, and ones that were high are now compressive. So before, if you look at the before scenario, actually I want the schematic. I'll go back to this a second. Basically, here are our two different scenarios that are what we have here. If we have on the build plate, we have the part, generally tensile residual stresses in the part. The build plate then takes up a lot of that load, and that's what essentially keeps this part fixed. So you have compressive in this region, tensile in this region, and then you remove the part from the build plate, and actually the regions that were the highest in tension actually flip and are now the highest in compression, and then the regions that were highest, or the lowest in tensile residual stress is now the highest in tensile residual stress. So where this part, this is kind of the cross section where this part is held flat. Before, primarily from the action of the build plate, and now it bowls up. And you see what you see from beam bending is that you have compressive stress in this location, tensile here. Right? So this is like you're taking some sort of beam, and now you're bending it this way. You're going to get compression on the top of that beam and tension at the bottom of that beam. And so these are kind of two different time points or configurations that are interesting to look at here. Going back just a few slides and talking about that a little bit. So this is just looking at this from more of a mechanics of materials point of view. In any beam bending problem, you have two things that you can calculate, and one of these must be satisfied. And so one is that if we look at a single face here, we know that the sum of all forces in that x direction, those all have to equal 0, right? Given that this is static, it's not moving, right? So if they're not equal to 0, it's going to have some sort of dynamic reconfiguration of the system until it settles down to something that is 0, right? And so that would be this equation here. If we look at the stress, with individual stress on a small unit cell, if we do a summation over the entire area of that cross-section, we should get 0. We can also calculate the moment, or equivalent moment, to keep this in static equilibrium as well. And so that is the moment coming from the other part of this beam that's not here, but you would have from this central axis, and this is going to be actually the center of gravity of this cross-section, you can calculate the moment about that center of gravity. And so that is simply looking at what is the residual stress multiplied by its moment arm, which is y, and you sum them all up in the instantaneous moment. So these are the two things that we have to concern ourselves with here. If you, going back to this idea here, when this is in static equilibrium on the build plate, basically all the summations of all the positive and negative stresses have to equal out, weighted by their area. And now, of course, on the build plate, this is usually considerably larger than the parts we're talking about. So this is probably not a good representation. This should probably be taking up a larger portion of this. But we should have equilibrium where all these positive and negative compressive stresses balance each other out. When we remove it from the build plate, this build plate no longer comes into play, right? It is now two separate structures. And so you have to have a balance in the stress here. Now, if we were to look at this from purely a beam bending problem, you'll see that the neutral axis is always at the center of a beam of when we have uniform cross-section. It's not so neat and clean when we have actual experimental results and actual parts, but we have reasonable amounts of that. You can see that at the center, this is Z equals 2.5. This is a 5 millimeter thick part. We have some areas that has negative or compressive residual stress, and we have some that are positive. So there's a kind of an approximate, on average, the center is somewhat this zero stress plane. So it's not a plane, it's more like a manifold. It's a little bit more complicated than, it's experimental data. It's not as simple as a beam emitter problem. It's a good approximate. Okay. Does that kind of make sense of the balance that has to happen here? Okay. So I'm going to go through an example that I hope maybe clears this up a little bit more. So example 9.4. So we're saying that we're looking at two different configurations here, and I'll give motivations for the functions that were defined in a second, and show how that matches some. These are really clean functions that we can integrate to actually understand what is the deflection, and I'll show how these somewhat represent things that you see in the experiments in terms of residual stress levels. So if we look at what this says here, is basically saying we have a stainless steel bar of length L, width B, and height H, and it's originally held to a build plate without deformation. So that's never going to be true. There's going to be some deformation. So even though it's held to a really thick plate, there's still going to be some deformation because the material can yield, all these other things that happen. But this is creating a residual stress because it's being held in some sort of taut or flexed position. Means all the residual stress built up. And so what this equation is saying is that we have a beam so this beam is of width B. It is of length L. And height H. Okay. And it's saying that along the x direction, the residual stress varies as a cosine function. So it's in the x direction, it looks like this. Okay, and I'll draw this and let everyone draw this and go back to some experimental data that approximately shows this. Just note that it's easier to look at this if you consider 0 to be the center of this beam in both the x direction and y direction. So make sure this is clear. This is x, this is z, this would be y. Okay, so that is how the function changes in the x direction. To kind of motivate that, if we look at the residual stresses, essentially 0 at the edges on the build plate configuration, and it's highest in the middle, right? Kind of like a cosine wave. Okay. All right. In the z direction, what we're saying, if I were to cut at this cross section, say in the middle, and now I look at it from this direction, all right, what I'm saying is that we have tensile residual stress, and it has this shape. And this is approximately satisfied or approximately corroborated with experimental data that our group and other people have taken, and also matches what some of the really basic residual stress theory in terms of how thermal contraction expansion yields to residual stress in a part. has a fairly linear relationship. And so that would be this part here, where keep in mind that z is equal to 0 is all on this neutral axis. Or not neutral in this case, but the center of this beam in terms of a moment of inertia perspective. Okay, so that's what this function is basically saying. So this is on build plate. All right, once it's released, it has a maximum stress of sigma 1 bar. All right, once it's released, it has a different residual stress profile. So again, we'll draw beam again. All right, and so it says the residual stress profile here is in the cross section. This one's probably the easiest to show first. This matches with the schematics we had before. In the cross section, we are going to have compressive stress. Let me make this larger, it's a little too small. Okay, so compressive stress at the top, and then tensile stresses at the bottom of the part. That's represented by just this linear equation, where if z is equal to 0, that'd be the neutral axis, where we had no stress. This function in terms of x means that the stress is approximately 0 at the center in terms of the x direction, and then it gets larger towards the edges. So this matches the profile we saw. Approximately 0 on the center, larger towards the edge in terms of residual stress. All right. Everyone good with those kind of assumptions and so, okay. So then now the question is compute the deflection of the bar after it is released. Okay. All right. So if we know beginning state, end state, can we compute the deflection of this bar? Try to understand this. Okay. So the first thing we have to do is we have to compute the moment in the bar for these two configurations. So the moment is again effective moment in terms of the moment at each cross section, and we can compute this along the length. So we get a moment in x direction. So the moment going from equations like this right here, again, it's just the stress times the moment arm, dA, right? Okay, so if we want to look at the moment in the x direction for configuration 1, we'll call this m1 of x. All right, so this is the stress in configuration A, and then filling in what the stress is, we will get negative sigma 1 bar B. What else is going to pull out? The integration is not going to be with respect to x, so we can pull out the cosine pi over L x, and do integration between negative h over 2 to h over 2 z squared over h plus 1/2 z dz. Okay, so then integrating this function, this. Okay. All right. So when we evaluate then this at the two limits integration, the z squared term is going to go away. That's because we're putting in an h over 2 and a negative h over 2. If you square that, you get exactly the same thing. You subtract the 2. This term is not going to go away because this is equal to a third, so the negative sign is going to matter. So we get an equation for the moment of this. M2, similar procedure. Okay, then we integrate this. I'll skip to the chase because this is just integration of a pretty simple function, just z squared, right? And we're going to get this right here. Okay, so everything's good? Okay. Okay, so now we have the moment in the beam in two configurations, right? We have a moment when it's the moment inside the beam. This is not including the moment coming from the build plate below it, right? That's actually doing a lot to hold this in a flex position. So the moment in the beam went on the build plate, moment on the beam off the build plates. Just to make sure this is clear in the notes. On build plate, off build plate. Okay. So we can, from this though, we can understand what is basically the moment being provided by the build plate itself, right? By taking the difference of this. So moment provided by build plate. So this would be m1 of x minus m2 of x, right? This is essentially what the build plate is putting on this beam to keep it in the stressed or the highest stress configuration to keep it from being deformed, right? So if we want to know then, in an equivalent sense, we want to know, right, what would the equivalent moment have to be applied to then deform it? It would just be the negative of this. You can think of this either I release this moment, or if I want to know how would this be deformed, I can apply the negative of that to see what the deformation of that beam is going to be. So if I say conversely, the moment released when beam released is m2 minus m1. So if I want to know then what m2 minus m1 is, it's just plugging these two functions in. I'll save you some of the math, but this is just simple addition. This is going to be BH squared over 12. This whole quantity, which is a function of cosine. And then this offset here. Okay. So now that we have it in this form, then we can turn this into a pretty simple beam bending equation, right? This would be essentially the moment that is applied when we go from, it's a difference in moments, but it's a moment that's applied, they go from the undeformed configuration to the deformed configuration. So it turns almost exactly like the problems that we saw on Tuesday's lectures of beam bending. And so from here we can compute deflection of beam. So remember that the curvature of the beam is equal to the moment. So the curvature times the modulus of elasticity times the moment of inertia is equal to moment, not just the curvature. Okay, so from this, if I want to get then the slope, or the modulus of elasticity times inertia times the slope, I integrate both sides, right? So if I integrate once, this gives me EI times the slope, and then I have to integrate this function. So integrating this function, I have a function in cosine, right? So this is going to be positive BH squared over 12 L over pi, because that's the argument of this cosine function. I'm going to bring all the coefficients out front here. All right, and then sine pi over L x. Next term, integrate this function with respect to x. That just multiplies by x. And constant of integration, C1. Next, if I want to get deflection, that's integration again. Okay, just do the same thing. Now I'm integrating a sine function that turns into a negative cosine. Another L over pi comes out, so now I have L squared over pi squared. And then we get a cosine function again. Okay, C1x plus then C2, another constant of integration, right? All right, any questions about that? Okay. Boundary conditions, so just going back to this beam right here, this is the discussion I had on Tuesday, is that this is not the problem that you typically see with beam bending where you have some sort of support conditions here. This is now just a bar in space. And so we just have to compute deflection relative to some way in which we're holding this bar. Okay, so the most logical one is you say at the center, I hold this at a datum of 0, and I say that at the center it has a slope of 0, and I look at deflection relative to that, right? So that imposes then a boundary condition of BC's at deflection, sorry, the angle, or slope, I mean, at x is equal to 0 is equal to 0, and then deflection at x equal to 0 is equal to 0. All right, so if I have those two boundary conditions, I can go back and look at this. All right, so if I say that the slope is equal to 0 at x equals 0, this is the slope equation, right? So left-hand side is equal to 0. That means right-hand side is equal to 0 somehow. Sine of x, 0. X itself, 0. That must mean C1 is equal to 0, right? All right, so deflection is equal to 0. This one goes to 0. This one does not. This one goes to 1. In terms of the cosine term, so it's this whole coefficient. This term goes to 0. That means C2 has to equal the negative of this coefficient, right? So C1 is going to equal to positive BH squared over 12, L squared over pi squared, 2 sigma 2 plus sigma 1. So we get C1 is equal to 1, or C1 is equal to 0. C2 BH squared, L squared over 12 pi squared. All right, now putting everything together. Deflection, then, I can move the modulus elasticity and inertia over to the right-hand side. All right, and I get this equation. All right. So then we can start to look at applying this and trying to understand some relationships here. So the next slide is going to show a plot, and it's going to show a plot with the case. All right, sigma 1 is equal to 350 megapascals. So keep in mind this is the highest stress seen in this part for configuration 1. Sigma 2 is going to equal to 100 megapascals. So remember, there's a stress relaxation when the part is released from the build plate, and this is the highest stress seen in the part measured experimentally. L is going to be equal to 45 millimeters. H, we're going to go through a few different H's. H is going to be 1 millimeter, 5 millimeters, and 10 millimeters to see how this affects things. And then B is going to be equal to 10 millimeters. And this is stainless steel from the problem statement. Okay. So here are the two plots. So the first one is the moment we calculated. So moment 2 minus moment 1, right? So this is the moment that's actually doing the bending of this. What you can see here is that the moment, the larger the structure is, the larger the moment is going to be, actually. Right? That's because your moment arm is going up. Right? So for very thin structures, like a 1 millimeter thick beam, that's a really thin beam, you get a moment that looks almost minuscule compared to when you get larger heights in this structure. But you get somewhere maximum around 30 Newton meters, which is a lot. So stress levels, this is considerably high stress levels. I calculated that when I was working through this problem, somewhere around the range of 200 megapascals. So it's a lot of stress in the part. At this, but it's thick. It's a pretty big chunk of stainless steel, right? So it actually has the ability to resist that quite well. This moment in the very thin member is quite small, but you get a ton of deflection because of how thin it is, right? You have a very long beam. You have basically an aspect ratio of the height is 1 millimeter and the length is 45 millimeters. So you get a pretty considerable amount of deflection in this beam, getting close to around a 0.5 millimeter in deflection at the edges, right? For the thicker structures, you're getting on the order of 50 microns deflection. Nate, yes?
Also, curiosity, is there a way to undo this deflection, or are you just out of luck if this happens?
So,
By pressing it or something?
so the best way to handle this, and this is going into the, actually 2 slides from now, is to handle it before you remove it from the build plate with the stress relief. So I think, so a lot of, pretty much any process right now, they are doing stress relieves on this. That's an expense that people don't want to do, so there's a lot of motivation to get away from having to do a stress relief in your part, and that's going down to process design. But if you're not to do a stress relief, you almost inevitably are going to get reasonable deflection. So it depends on what your manufacturing specifications are. 50 microns may be acceptable to you, it may not be. All right. It depends. That's pretty small though. That's getting on the order of the roughness of your part when you get to 50 microns, right? But getting close to a 0.5 millimeter, I think that's out of spec for a lot of engineering requirements, right? That's pretty high. Yes?
Would it be possible, like, if I'm building a thin part, I'm able to like measure deflection, build it onto like a curved surface, so that once you take it off, it'll deflect to be a
So invert it?
yeah,
yeah.
like the build plate is.
Yeah, so there's an America Makes call to do just that. I don't know, I haven't really followed up with who won that award and how well they did with it, but they wanted to predict what the distortions were going to be and not building on a curved surface, but building the inverse of that distortion, such that when it does distort, it gets you the part you want. I haven't followed up to know whatever happened to that, but people have been looking into that, and I don't know how that turned out or not. Yeah, but it's been postulated. So this is still, I mean, like everything here is still pretty new in terms of like design. Like additive manufacturing is changing pretty fast, and I would not be surprised if someone figures that out pretty soon, if they haven't already. Okay. So then, so these are the type of deflections you get, and then kind of segueing into countermeasures for this. Kind of going back full circle here, we discussed that in the beginning of this, we discussed that temperature gradients are the primary driver of residual stresses. Right? So a lot of the efforts have been, how can you reduce your temperature gradients when you're building this part such that you don't have such high residual stresses. So 2 things to note, things that I've worked with and what the field is mostly using laser powder bed fusion type systems. And those have environmental temperatures of somewhere in the range of 2 to 200 degrees C, but metal melts at the temperature it melts, right? And there's no, regardless if you're using a laser system or E-beam system, you're still using the same types of metals, so it's going to melt, and whatever the melting temperature of that materials is on the order of 1500 degrees C, right? Somewhere in that range. So the advantage of a lot of these E-beam systems is that they work at really elevated temperatures in the 600 to 1000 degrees C range, and so your residual stresses that you build in the part are considerably lower with E-beam systems. Also, there was discussion on Tuesday about the FDM or melt process-based ME. Do you get residual stresses? How appreciable is that? You definitely do, but here again, your temperature gradients aren't quite as high. You're talking about glass transition temperatures being on the order of 150 C, environmental temperatures in the ranges of 25 to 80 C, right? So you're only talking about somewhere around 100 degrees C differential, where in laser powder bed systems, you're talking about the order of 1000 degrees C differential between your cold areas and your hot areas. So you get considerable residual stresses in those parts. So how this manifests in terms of residual stresses, this is a work where they're basically looking at printing exactly the same coupons or parts, but one of them using a laser powder bed fusion system and one using electron beam powder bed fusion systems. So this is using, like, say, concept laser system versus an RCAM system. So this may be a little difficult to read. The main thing to point out here is the preheat temperatures. So preheat in the E-beam system of 950 C, 1200 Kelvin, and the DMLS, which is laser powder bed fusion system, this is none, this would be room temperature, right? So 25 C. And this, obviously, everything is different. You have a different system, you have to do everything in a different manner, but the main thing here is the preheat temperature. And so you can then look at the residual stresses in these parts. This is in the X, Y, and Z direction, and I think the most important thing to look at here is the scale bar, and unfortunately the scale bar, this is terrible resolution in the E-beam system. Let me rectify that really quickly. Just so I want to make sure this is quoted correctly. Okay, who's the author? Some really strange name. Okay, so I'll zoom into this so you can see it better. So the other heat map bar went from negative 500 to positive 500 megapascals. And so, I don't know, is this showing up very well on the screen over there? No, it is, okay. So just to note, the scale bar here is going from negative 100 to 100, right? So about a factor of 5 difference in the residual stress when you have really high preheat temperatures that you get with the E-beam system. So that's the main message here, is that considerable reduction in residual stress by operating at higher temperatures, which you can do with E-beam systems. All right, and then the last thing, there's been discussion about, can you remove the residual stress via heat treatment? And this has been the most common way in which people get rid of this residual stress and then keep distortion from being unmanageable. And so this is via some sort of post-process heat treatment. So here's an example from a work that does a direct comparison of residual stresses. This is using basically the hole drilling method, which is very close to the crack compliance method that Ryan presented on. It's the same basic idea to look at residual stress. And this is just a very stereotypical heat treatment profile where you put the part on the build plate into a furnace and you take it up to somewhere in the 650 degrees C range and you hold it there for 9 hours. Okay. So heating up something that hot for 9 hours costs a lot in terms of energy. So if you are General Electric and you're pumping these things out as fast as you can for airplanes, you probably don't want to have tons of these furnaces running, but I mean, they're also casting parts and doing other things that are really energy intensive as well, so I don't think it's detrimental, but this is something that people are looking to try and eliminate from the process, because you're already pumping in a lot of energy just to melt the material, and then having to do something post-treatment is expensive as well. So this would be a type of profile that you'd have, and then here is residual stress in the part in the as-built case, and then the stress relief case. So you can see a huge decrease in the amount of stress in the part when you do this post-process anneal. So this is on the order of 1,000 megapascal decrease in residual residual stress. I'd have to look at this material and trying to figure out what type of material they're getting 1,000 megapascals. All right, now I'm not necessarily believing these results. I want to read this paper again. That's well above the yield stress of a lot of materials. So I'll have to look and see what material that is. Yeah, sorry about that. I didn't think of that when I was making this slide, how high that is. That seems crazy. But we'll double check that. The main thing here is a large reduction in the residual stress in parts via some sort of heat treatment afterwards. And then when you, of course, cut it off, then essentially no residual stress, then you should get very little distortion. Okay. This is the end of this module in terms of relationships between residual stress, temperature, distortion. Any questions on any of that before we go into a brief systems integration control module? Yes?
I'm not too familiar with the whole drilling method, but is there any reason that with stresses that high, we see an appreciable increase in the error, the deviation or error mark?
I'm not too familiar either. The only thing in terms of if you look at this purely from a signal to noise ratio, as your signal goes up, your noise goes up as well, right? So that's the only thing I can think of off the bat, but I can't answer any better than that. Okay. All right, like I said, after this, I'm heading to my office. I'll be there for a while. In case you have any questions on the homework, please stop in. If you're not available right now because you have other classes, etc., feel free to send me an email. All right. See you on Tuesday, if not before then.